Hello and welcome to my class. I'm Grolin Annalisi from ThinkMO Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is switch principle, VLAN and VTP. Let's talk about the technical knowledge of the exchange network from today. As of last class, we have already finished talking about routing knowledge. Includes static routing, IGRP, and OSPF. Before we formally explain the technology of the exchange, first of all, we need to develop the entire network. Make a simple understanding. Because when we talk about exchange today, we must mention a device. Is the switch. So how did the network evolve step by step into what it is now? It is known intranet. Switches are very common. Even switching technology for enterprise networks is much more common than routing technology. Then why should there be such a technology? Including how the switch has evolved. I'll draw a picture to explain. Assuming these are the original two PCs. At the beginning, how should the two PCs be connected? It is known. A device wants to transfer data with another device. They are connected by a physical transmission medium. Actually, before the web, all computers are standalone. At that time there was no network cable, no network card, no protocol stack. The overall data transmission is through CD and floppy disk. After a period of time, with the innovation of web records, the network cable appeared. Network cable as physical transmission medium. We can pass data in the middle. Secondly, there must also be a network card on each device. Like switches and routers. The interfaces on them are called network interfaces. The one on the PC is called the network card. Then network cable plus network card. Plus running the same protocol stack on the device. That is what we call the TCP/IP protocol stack. These three constitute an element. We call it the smallest network unit. They can officially start data transmission. I give a simple example. For example, now this cable carries the overall bit stream. That is electrical signal. Similar to when we call in analog signals carrying voice streams such as. They are responsible for the transmission of signals. Then for the network card. After the network interface receives the incoming bit stream, it converts these bit streams into data. Sent to the protocol stack for processing. Including when it sends data to the outside world. It is also the network card that converts the data into a bit stream. And then sent out. That's like the TCP/IP I just mentioned. I mentioned this when I talked about the reference model before. We are talking about OSI. But actually we are using TCP/IP now. They are equivalent to communication language between multiple devices. That is, in the process of realizing the communication, including analysis of the data, addressing including future addresses. Because the three layers can do addressing, including our control over data traffic. All the same. Here's some of what it does. But with the development of the network, slowly there are problems. Between two PCs. We can't keep them close together forever. Network communication cannot be one computer to one computer. They are very close. Sometimes, we're going to involve some remote data access. Then there will be problems. The transmission medium such as network cable has the upper limit of transmission. The longest effective transmission distance of the network cable is 100 meters. If the two computers are too far apart between the terminals, Once the transmission limit of this network cable is exceeded, then the data starts to be lost. This is what we call lost packets. Your data signal is unstable. Data can be passed, but there will be packet loss. So not now. We will have a way. Add a repeater between these two devices. Just give it a signal amplification in the middle. I draw a device here. This is the repeater. The relay season can complete the amplification of the data signal. Equivalent to. The repeater has received data here. After receiving, it's going to be an integration. Then amplify the signal. Send the signal again. Then it can extend the transmission distance of the network cable. But this device has a problem. That is, it has only two interfaces. It has fewer interfaces. Two interfaces are not enough, because it can only amplify the signal of two devices. Look at me as an example. It has only two interfaces. It won't work if you connect another device here. You can't connect a third device. So there's the next generation of devices. After the repeater is the hub. To us, the two interfaces of the repeater are not enough. Let's change a device now. Called a hub. We still put it between the two devices. Then it is called a multiport repeater. It's no different from a repeater overall. There are more interfaces. So, we put it here now. This is a multiport repeater. A multiport repeater means it can now connect to more devices. Then we can complete the data interaction between multiple devices. Let's briefly talk about how it works. If the hub is now from an interface, received a data, it will directly send a copy from other interfaces. So it's a repeater. That is a working principle of multiport repeater. Well, first thing to know. It is a device working at the physical layer. Actually, it will only perform simple flooding processing on the data. This flooding refers to it received data from an interface. Copy and send a copy of other interfaces. For example, now this PC1 wants to access PC2. Don't want to access PC3. Then this data cannot be forwarded only to PC2. It will definitely send a copy to PC3. Because it handles all data. All other interfaces send a copy. So the hub does not recognize some of the upper layer. IP address or MAC address. So, it has no way to isolate the terminal. Everyone should know this. In fact, this kind of bandwidth utilization is relatively low. Because the bandwidth of the link is always occupied. Second, data security cannot be guaranteed. Hub-based networking. Unicast communication is not possible. So that's one of its downsides. We also call this device a hub. Half-duplex device. When you send, others cannot send at the same time. I should have mentioned a concept to you before. Collision domain. The data is within a certain range. If in the process of sending, data collision. This is called a collision domain. Then the half-duplex environment we are talking about is a typical collision domain. Now PC1 sends a data. In the process of sending, this PC3 cannot be sent out. Otherwise it is in a collision domain. The data will be incomplete. The data will be transferred from the original 0101. May be lost in the middle. A few digits are lost or become garbled. It's not complete. So this kind of networking environment is not okay. The transmission utilization rate is relatively low. Of course. We also said before. There is a technology in the conflict domain called CCNA/CD. It can solve problems in conflict domains. But it's too inefficient. So slowly we will find. We want to amplify the signal in the middle. I also want to connect multiple terminals in the middle. Also hope the collision domain isn't that big. Now there is no way to solve this problem. So how to solve it? We came out with a new device. The new device is called a bridge. A bridge is a small switch. You can understand it as is a data link layer product. Works on the second floor. The bridge has two interfaces. For the bridge, different interfaces are different collision domains. There will be no data conflict between the two interfaces. Let me give an example to explain the differences between bridge-based networking and hubs. For example, these two are bridge interfaces. In the meantime, they can send and receive data. Non-interference between the two. We can do this kind of work through the bridge. But the bridge itself has its own common problems. It also has only two interfaces. So the network is like this. A bridge in the middle. Connect two hubs next to a bridge. Then go to connect multiple terminal PCs. We can do it this way. To isolate the conflict domain on a smaller scale. You will find. Because this is the hub. So this is a collision domain. But since this is a bridge interface. So actually, collision domains are only so big. Probably originally 6 PC conflicts. But now you turn 6 PCs into 3 PCs conflicting. One of its problems is that it has only 2 interfaces. So the number of interfaces is not enough. Then the switch appears. A bridge works like a switch. It differs from the switch in that there are more switch interfaces than. We'll talk about how switches work in a moment. The latest products are now available. That is the switch we are using now. Suppose now this is a switch. What can a switch do? First of all, it has many interfaces. I can now connect other devices to this switch. I mark these PCs. 1, 2, 3, 4. 4 devices. Let's say this is the 4 interfaces of the switch. 4 switches. How does it work now? First of all, the switch is also a product of the data link layer. Works at the data link layer. There is a very core parameter in it, called MAC address. The switch can record the MAC address of the terminal, and can generate a table on itself, called MAC address table. What is stored in this table? For example, now interface 1 of the switch corresponds to a PC1 below. Suppose the MAC address of PC1 is a. It will generate such a correspondence. Let's say this is interface 2, interface 3, and interface 4. It is possible to store such information locally, followed by BCD. Their MAC addresses are ABCD. A table like this will be generated on the switch. Since it has a table like this, it can complete a precise forwarding of data. If now PC3 wants to visit PC2, the MAC address of PC2 is B. Then it's making a data request. Do you still remember the ARP we learned before? We can request to the other party's MAC through ARP. Complete data encapsulation. If PC3 now has the MAC address of PC2, it sends a data to the switch. The switch sees that its destination MAC is going to be. The switch will query the local MAC address table. It is found that B corresponds to its interface 2. Send data out from interface 2. Then this data came to PC2 alone. Then this data is for PC1 and PC4. They won't accept. The switch can complete unicast communication. And the switch is a full duplex device. The interface of the switch can isolate the collision domain. All devices can send at the same time. And receiving data is not affected. So in fact, you can understand the switch as combination of bridge and hub. A hub is multiple interfaces. There is also a MAC address table in the bridge. Works the same as a switch. It's just that there are few interfaces. It is an advanced hub plus a bridge equal to a switch. All in one. In the end, it became the equipment we use now. Same. Within each company. In fact, they are all similar network structures. If you want one company to communicate with another company, it is impossible for all devices to be connected to the switch. Including that we are now connected all over the world. It is impossible to network through switches. That's why we have such routers that are farther away and based on route forwarding. Eventually connect. This is the development of the web. I just want to tell you how the switch came from. Then we will start to formally talk about the content of the course. Today we talk about the principle of the switch. Here is a word. Ethernet devices including hubs and switches. These are the two most typical devices. Let's do a brief review. We just talked about hubs. For devices such as hubs, everyone must first be clear. Under what circumstances should we use such a device? I give an example. There is a PC down there. Multiple PCs now. Suppose a company. The number will definitely increase. Because the number of employees will increase. Everyone needs to communicate with each other. Everyone is on the same network segment. If you want to connect multiple devices. Middleware. So the first hub appeared. Connect multiple devices. The hub was the first of its kind. We use this device. Start connecting. After connecting, we need to know what the hub is based on for data forwarding. I just told everyone. It will perform flooding when it receives the data. But why flooding? How did you know? The data forwarding of the hub depends entirely on its current interface card. Under this interface, you can feel the voltage swing value under the interface. As long as there is data going through. Under the interface on this line. I feel that the data is coming now. Then the hub will receive. And carry out flooding. Bridge is a name. It is a switch with only two interfaces. The processing action of the hub for data is flooding. Flooding means that the data ports other than this receive port. Copy all and send a copy. Here's how it works. So when the hub forwards, no matter what the data, it doesn't care where it goes. As long as the data comes, it will flood out. So actually, it cannot be called a network device. It is just a product of the physical layer. Because it has no CPU. It does not need to calculate. This is how it forwards. And let me emphasize one more point. We also said, if the data sent by PC1 is now, send it to PC2 here. It cannot be sent out at the same time. Data conflict. Therefore, the work efficiency of the hub will be relatively low. The concept of conflict domains we talked about before. We won't talk today. Today we mainly talk about switches. The abbreviation is usually SW. Switches work differently than hubs. Based on physical hardware. Everyone must first remember. For switches, each interface of a switch is a collision domain. Different interfaces are different collision domains. Then it means collision domains are actually small at the same time. There is only one line like this. So now receiving and sending data has no effect. PC1 sends data. PC2 can also send. For switch ports, you don't need to understand why it is different from the interface of the hub. This is an improvement based on physical hardware. That's what's on the hardware level. We only need to know its logical concept. And the switch's interface has a behavior. Self-negotiation behavior. Its interface can realize the negotiation of working mode. For example, the switch is connected to a hub. The hub interface is a half-duplex mode. The switch is in full duplex mode. Switches can be compatible to small. It can also be turned into a half-duplex mode. This switch is connected to a switch. The peer interface rate is relatively small. Its interface rate is relatively high. It can accommodate the other. Negotiate to a rate consistent with it. Backward compatibility. Therefore, the interface of the switch can be negotiated automatically. Each interface of the switch is independent. Then please pay attention. Once each interface is independently, it means that the data of one interface of the switch will no longer be perceived by other interfaces. So how does it work? How to forward data? We just mentioned the MAC address table. For switches. Actually, it's like a brain. This brain is the MAC address table I just mentioned. I'm going to make a logo for the PC. This is PC1. The MAC address of PC1 is AA. This is PC2. The MAC address of PC2 is BB. This is PC3. The MAC address of PC3 is CC. This is PC4. The MAC address of PC4 is DD. Let's simulate data sending now. Suppose PC1 wants to send data to PC2. Then they have to complete an encapsulation of the source MAC and the destination MAC. We talked about. There are two encapsulation methods at the data link layer. One is called E2. One is called 802.3. What we use most now is the E2 package. Now the data link layer is going to be encapsulated. The encapsulation is the Ethernet 2 standard. It has a parameter in it called SMAC and DMAC. Source MAC and destination MAC. Now PC1 is going to visit PC2. Source MAC is AA. The target MAC is BB. Then if such a data is generated, prove that they have made an ARP request. Already got PC2 MAC. This data wants to be sent to the switch like this. Then let it help perform the forwarding. For switches, it received a data. First it has to learn the MAC address. That is, the switch will record the source MAC of the received data frame and the information of the incoming interface. Now this data is sent from this PC. Enter switch. The interface of the switch itself is numbered. For example, this is the interface 1, interface 2, interface 3, interface 4 of the switch. It learns locally. It only needs to receive a data from this interface. It will look at the source MAC in this data and record it in the local MAC address table. So it will now record a interface 1 corresponds to the MAC address AA. It learns like this. The first behavior after it receives the data is called learning. The next behavior is to forward. For forwarding, now it behaves differently. If it receives a data, it is a specific device to be sent to. For example, now it needs to be sent to PC2 specifically. Then it will look at the MAC address table locally. If the MAC address table has, then just retweet. There is a parameter in the MAC address table. Known unicast data frame. Unicast means this data is sent by PC1 alone to a certain device. That is, sent to a certain MAC address alone. And look up the table. If there is, it means that this data can know a clear destination. Known unicast data frame. If you know it, directly look up the table and forward it. What if you don't know? Now it's going to BB. But this doesn't have this BB. Then what should we do? If there is no that for this switch. Unknown unicast data frame. Now where does this data frame go? It doesn't recognize the purpose MAC. So now it will perform flooding. So if a data really comes now, it doesn't recognize the destination MAC. Then it will perform flooding. The action of flooding is to send a copy from all other interfaces. It's the same as the hub just now. It will also send. But you have to pay attention to the difference. The difference is that if there is one in the table, it will be unicast forwarded. Flooding if there is no table. If flooding, PC2 received. It will reply after receiving. When replying, this data enters the interface of the switch again. It learned again. After learning, its MAC address table can be filled. Then next time when the PC sends it again, it can look up the table and forward directly. This is how the switch works. Received a unicast data with a very specific destination. See if there is such a purpose MAC in the unicast data table. Check the table if you have. Flooding if not. After flooding, the device has finished learning. You can check the table next time. This is a processing action for unicast data. We may also have some broadcast messages. Suppose the destination MAC is now all F. When PC1 communicates with other devices for the first time. But I don't know the MAC of other devices. It has to send an ARP broadcast. Then on to the switch. The switch has received a broadcast data. Then don't think about it. Absolutely direct flooding. So you will find. The switch will also perform flooding. But it's not mindless flooding like a hub. Received broadcast or unknown unicast will cause flooding. If you receive a known MAC in the table, it looks up the table. So this is one of the places where switches are better than hubs. It has a forward appearance. Multicast we are not discussing now. Radio is for everyone. Multicast is for a certain group. So if the switch does not enable any functions related to multicast. In fact, it does not know whether the equipment below is added to the group. So you can temporarily consider it the same as broadcasting. You will learn multicast when you reach the IE stage. We don't learn this technology now. Let's make a brief summary. For switches, it doesn't actually care about the IP address of the device. It does not care what network segment the device is. It only sees the second layer when looking at the data. Switches work at the data link layer. That is the second floor. Routers work at layer 3. After it receives a data. To decapsulate the message. To which level? If it demolishes the second floor. After reading the lookup table. Re-encapsulate the second layer before forwarding. Then it means that you only look at the content of the second floor in the whole process. Don't look at the third floor. This is called working on the second floor. For routers, after receiving, must see the second floor. First of all, the destination MAC is sent to it. Yes. Look at the third floor. In the third layer, we need to look at the destination IP address. Then perform corresponding routing function addressing and forwarding. So a router is a router that works on layer 3. For switches, work on the second floor. So all the IP-related stuff at layer 3. It doesn't care at all. Here are some differences between switches and routers. When we talked about routers earlier, basically all related to IP. The switch is not related to IP. I will make a simple explanation. If the interface of the switch receives a data, then it finds this data. It needs to be sent out from this interface. Then the switch will perform an action at this time, called discarding. It doesn't want this packet. So under what circumstances would such a behavior occur? We will not explain at this stage. When you reach the IP stage in the future, you will learn about layer 2 loops. When you encounter a loop, can understand this sentence. Certainly. If it receives a message, failed to pass the verification of layer 2 FCS, it also drops. So actually the switch it works is simple. or retweet, or flooding, or discard. Let's take a look at the PPT's explanation of this. Let's sort it out. The first is flooding. Under what circumstances will we flooding? The switch received a data from an interface. If this data is a broadcast data, the switch is directly flooding. If the data is a unicast data, and there is no corresponding destination MAC in the MAC address table, then exchange chance flooding. So what is forwarding? The switch receives a unicast data, and there is this in the MAC address table. Then it forwards. And what is discarded? It's what I just told you. The switch finishes receiving data from an interface. Also send out from this interface. It will discard this data. This is the switch forwarding behavior. The switch also has a working behavior called learning. That is, learn autonomously. The switch can learn automatically. You don't have to configure it. So some people will say that the switch can be used when it is turned on. You don't need to configure it. That's why it works by itself. Here's some of how the basics of the switch work. Next, these are: forward data frame, the initial state of the switch, learn MAC address. Let's take a look. Just started without a MAC. Sent a data. Learn the MAC under interface 1. Then broadcast. This is an ARP request. Obviously sent. Host B replies to host C. Learned host C under interface 3. This is the MAC address. It's the same as the picture I drew. It's just that it's painted more professionally. Next we start talking about VLAN. VLAN is called Virtual Local Area Network. V is virtual. LAN is local area network. Why do we have a virtual local area network? Let me first describe an environment. In the future, many devices will be connected to one switch. Suppose a switch is connected to 40 devices. Let's just draw. 40 devices is a lot, because the switch has 24 ports and 48 ports. For example, now a device is infected with a virus. This virus is flooding by broadcasting. Then it will infect all other devices. That is, it now affects other devices intermittently, regardless of whether it is in the same department or not. Everyone is connected on a switch. It causes all devices to infect. For the company's internal, everyone will find. In daily life, some of our businesses also need to be quarantined. I give a simple example. For example, your company's R&D department. Usually there are some research and development data or some samples stored in internal server. There are some PCs in the R&D department that cannot even connect to the external network. There will be a lot of core data in it. For business, any PC is now connected to a switch. Actually, we are exposed to the possibility of information leakage. It's all very common. So everyone will find. If all devices are now connected together, connected to a switch, then relatively speaking, there will be a security risk. Whether it is a security risk, or for our business isolation, the actual demand between departments is not well controlled. We have another solution. Just get a separate switch for each department. When you study, you will have this idea. In fact, this idea is correct. Indeed. But it's that expensive. So often we say from the perspective of cost saving, we prefer to buy a device. Just be able to get the job done. So for us now, we just want a device. Can do some of our traffic isolation. For example, a host has a virus. Less impact on other devices. Same. 40 hosts now. Maybe 8 are from the HR department. 6 are from the sales department. 7 are from the technical department. The business between them can also be isolated. Can communicate directly with each other. But I want to ask you a question. When we were learning VLAN, is often the easiest to confuse with a thing. You may have heard the saying before. Different VLANs are different broadcast domains. There is no connection between different network segments. If you can figure out between different network segments, need to find a gateway across network segments. Going to the third floor is also impossible. Then it should not work on the second floor. Some may think. Just configure different network segments for the following PCs. For example, here is a PC. I am 192.168.1.1. The PC on the right is 192.168.2.1. The two of them don't understand each other. If I now draw different network segments for different departments, they are all connected to a device. They also don't work. VLAN also does not work. Different network segments do not communicate. I simply configure it as a different network segment. It doesn't work. So everyone should know. Communication between different network segments. We mean unicast failure. You visit 192.168.2.1 from 192.168.1.1. This is called unicast communication. Then it is the three-layer routing and forwarding. 2.1 according to the destination IP. To query the routing table on the gateway. Then forward. It is a unicast forwarding. Unicast does not work. If the unicast cross-network segment, you only communicate on the second floor. Do not configure a gateway for it. This is absolutely not going to work. But you need to know. Unicast fails but broadcast works. Now this PC1 sends a broadcast data. After the switch receives the broadcast data, its processing behavior is flooding. So as long as this data is a broadcast data, this data can reach the device. As an internal company, virus infections are often broadcast, rather than targeted strikes. Not trying to infect a single device alone. Usually broadcast. So in the form of dividing the network segment, there is no way to isolate real broadcast traffic similar to viruses. It has nothing to do with what kind of data is now. It is related to the forwarding principle of the switch. As long as it is a broadcast packet, even if you divide it into different network segments, where should this data go or where? Everyone can receive. So you have no way to solve this problem. We can only solve it by means of VLAN. Everyone should have an understanding of VLAN. The different broadcast domains it's referring to are. In the future, broadcasting will not work either. This affects the forwarding behavior of the switch. That is, VLAN is configured on the switch. Due to the configuration of the switch, then you can target different interfaces of the switch. Divide it into different VLANs. To control future broadcast traffic. The same is true for unicast traffic. That is, from which interface can all the traffic be sent out? They will not transmit broadcasts between different VLANs. So it can be isolated. I simply give an example. For example, now I divide this interface into VLAN 10. This interface is also VLAN 10. But this interface is VLAN 20. If this device sends viruses out in the form of broadcasting, then it can be broadcast from this interface. But this interface doesn't work, because they cross VLAN. Different VLANs are different broadcast domains. Packets from different broadcast domains cannot be sent out. This is the behavior control that the switch does. A forwarding behavior of its own. So the broadcast domain we're talking about actually means a delivery range of this broadcast message. So the interface of the switch Flooding is the default for broadcast packets. And I tell you, all interfaces of the default switch belong to the same broadcast domain. Different VLANs are different broadcast domains. But unfortunately, by default, the switches are all in the same VLAN. If you want to control it in the future, you need to configure it separately. Okay. What can you understand as a virtual local area network? I configured VLAN on this device. You can understand a VLAN as a virtual switch. I configured a VLAN 10 on these few interfaces. You can understand it as. Now physically you see this switch. It's like cutting it in the middle. For example, the 4 interfaces on the left are assigned to VLAN 10. You can understand that this is 2 switches. It's like cutting the switch in half. This half is a switch. The other half, for example, are all VLAN 20. Although you see it as a device, but actually it has split. You can understand it as a different switch. In fact, there are many ways to divide VLANs. For example, based on MAC, even IP-based, including policy-based. But the one we use the most in our projects, VLAN division based on interface. For example, I now have many interfaces on this device. 1 to 48 interfaces. 48 port switch. We can usually divide the 15 interfaces. From 1 to 15 to the technical department. 15 interfaces from 16 to 30 are assigned to the sales department. 30 to 35 these interfaces are divided into the personnel department. The rest will be allocated to the logistics department. Leave 1 or 2 interfaces for redundancy. This is called interface-based VLAN division. Suppose I assign the technical department to VLAN 10. I assign the sales department to VLAN 20. Assign the personnel department to VLAN 30. This is how we divide. We'll do the configuration later. Let's start with the concept. This division is artificially divided by configuration. Pay attention to my words. Artificially divided by configuration. That is, you need to enter this interface. Then divide it into the corresponding VLAN. Then this interface belongs to this VLAN. It's simple. Between different VLANs, unknown unicast data frames can be isolated. Broadcast frames can also be isolated. Data flooding will not pass through different VLANs. Then one might ask. These 15 interfaces are technical department. Then if there is a virus in one of the data or a PC, what about sending to other devices? Okay. They also get infected. But we narrowed down the scope of the infection as much as possible. Originally 48 devices may be infected. Now you have divided the VLAN. Only these dozen or so devices are infected inside. So narrowed down. It's not that you divide the VLAN. There will be no forwarding of the virus. That's not what it means. You need to know. What we have to do is control as much as possible. I mentioned the structure to you before. Access. Converge. Core. VLAN will be configured in the access below. We will configure gateways of different VLANs on layer 3 switches. But there is no concept of 3-layer division VLAN. This is the access layer switch. They will divide VLAN here. For example, this is VLAN 10. This is VLAN 20. In the future, we will be here on the aggregation switch above. The gateways corresponding to VLAN 10 and VLAN 20 will be configured here. But we will not divide the VLAN in the 3rd layer. VLAN is a concept belonging to the 2nd layer. So, this technique is very common in corporate networks. In the corporate network, switching technology is much more common than routing technology. Because every enterprise must have a switch. But each enterprise does not necessarily have multiple routers. This is the application direction of their technology.